so to replace me in the big family of today, I counted that I might have been Stan's 8th PhD student. That was back in a time where you could still count your PhD students. Now the family has grown bigger and bigger. So the question I wanted to talk about today is a question that I find very puzzling, which is that learning sometimes fails quite miserably. So Ed was very nice in making my introduction for me. I wanted to take this example of fractions also to honor one study that just came out of Stan's lab about how fraction is hard for our French children. So in France, children start learning about fractions in 4th grade, and then in this study, they went to see the study, the children a couple of years later, and found that these children had very huge difficulties just placing a fraction on a number line, which is supposedly something quite simple to do. But here you have 6th graders, so they've had 2 years of education about fractions. This is the distribution of their response when they have to place 3/6. Correct answer is the one that's pointed in light green, and it's less than 10% of the children who get that answer. And which means that, so probably these children they heard stories about pizzas, and they heard stories about sharing cakes and all this, and they got everything we could think of. So maybe, yeah, as Ed pointed out, that story of pizza is maybe not ideal, but it's still a valid thing. It's still something that relates these symbols of fractions to something that's presumably intuitive, and 2 years of that is not enough. And it's not, as Ed pointed out, it's not just a French thing. It's been found all over the world. It's been found to be very persisting. The burger example was very impressive. And it's not only a fraction thing. You find this kind of resistance to learning across a range of different topics in math and in science. And so that's the question to me. It's very puzzling as what could be the nature of the block that is such that it prevents learning for 2 years of time. And I personally don't feel that we have the beginning of the answer to that question. But maybe to start trying to think about it, it's interesting to think about what may be happening in the head of the children during these long periods of time where they actually fail to learn. And here, I think there is really two kind of stories, broad kind of stories that can be told. The first story is that learning is gradual. It goes little by little. And then under that kind of story, to explain why it takes forever, you'd have to postulate that there's many such little steps that little children have to go through. So at the end, it takes forever. A second story is one where there's only really one or a few steps, but those few steps are really hard to make. Which then ends up that what's illustrated on the graph here is something where each time there is a red star is an instance where a child tried to learn something, but somehow the process didn't complete, so it was failed. And under that kind of story, learning takes a long time because on average, it will take a lot of attempts before you get to one attempt that actually succeeded. And, well, if you look at the literature, most of the theories of concept learning, they're actually on the side of gradual learning. But then if you ask learners how learning feels like, many people will be able to recall one or a few stories where learning felt discrete, like they had a sudden Eureka about something. And perhaps there's this famous, one of the most famous recall of a Eureka story is one by Poincaré, a French mathematician. A story where Poincaré was being stuck with his math, and then he decided to go on holidays and take a trip. It's good to take holidays. And then this happened. At the moment when I put my foot on the step, the idea came to me without anything in my former thoughts seeming to have paved the way for it. I did not verify the idea, I should not have had time, but I felt a perfect certainty. And, well, Poincaré is about discovering math, but then if you look at the literature, there are stories like this about learning math. But to our surprise, there was not actually evidence that this kind of things happens really when you're learning math. So this is what we set out to test in this one project that we did with Charlotte Barrault, who was then a PhD student in my lab. So we wanted to ask that whether it's true that people really experience eurekas when they're learning math. And then in the event that we would be able to demonstrate that people really experience their eurekas, we want to ask a further question, which is whether this first-person experience that they have, is it really accurate? So does it really accurately describe something that really went on in their mind, or is it just an illusion? And so we built an experiment to study concept learning in the lab. The target concept that we used is the concept of geodesics, which is in geometry. It's something that generalizes the idea of a straight line to curved surface. So a geodesic, just like a straight line, is a line that keeps going straight ahead, just it can be applied to a curved surface. And here I have some examples. The wiggly line on the left, it's not a geodesic. You probably would have guessed that. It doesn't go straight. The big circle on the center is a geodesic. It goes straight, and that probably feels quite intuitive. But that one here, it turns out that it's not very intuitive for people. Most people think it is a geodesic when actually it is not. And in another paper that I won't talk about, we found that there is actually the reason why it looks like a geodesic is that it's because it's a planar line, and people tend to equate geodesics with planar lines. But that's not what I'm going to look at today. Today, we wanted to look at what happens when people try to learn about geodesics and overcome this bias. So we did this experiment with adults, so quite old babies today for me. And so very straightforward. We first verified that they had indeed wrong intuitions about geodesics. Then we gave them lessons to learn about geodesics, and lessons were something like that, where it was all the lessons had the same mathematical content. So it was telling you that the great circle on the sphere is a geodesic, and the small circle is not a geodesic, and using simple physical models to tell you that. So here, for example, you have a rubber band. The rubber band goes along the great circle, it doesn't go along the small circle. And then across people, they got between 1 and 7 lessons like this with different kind of objects, but still always spheres. And then after this intervention, we tested their understanding of geodesics. So for example, in this test like this, where they had lines and they had to tell us whether it is a geodesic or not. And then at the very end of the experiment, we asked them whether they had experienced anything like a Eureka during the course of the experiment. And with this, we made 2 main discoveries. First, we found that it is true, as rumor has it, that studying triggers Eureka experiences. So we found that our participants did report Eureka, but most importantly, these reports were related to our manipulation, how many lessons we gave people. So the more lessons you got, the more likely you were to have experienced a Eureka. So far, it's not saying that Eureka brings about learning, but at least it's saying that if you study something, if you study some math, then you'll experience this kind of Eureka moments. And so then we moved on to the second question. Are Eurekas really about learning, not just about studying? Are they accurate in some sense? And we found that indeed these Eurekas have some truth to them. We found 2 senses in which they are accurate. first sense that it is true that when you have an Eureka, you've learned more. This is really related to the definition of what it is a Eureka. You get a new idea, so if you get more new ideas, you should have understood more about the concept, and that's what happened, that people who had experienced Eureka did better in our post-test on geodesics. But they did better in a very interesting way. It was not all across the board that they were better, but in our tests of geodesic identification, we actually had 4 conditions crossing what's a geodesic, 4 types of lines crossing being geodesic, non-being geodesics, and being planar and being non-planar. And if you remember, all the lessons were about the sphere. Well, it happens that one of these type of lines doesn't exist on the sphere, geometrically doesn't exist. So during the lessons, they only learned about 3 of these kinds of lines, never about the 4th one, the geodesic non-planar. And it's actually on this type of line that we saw the effect of having a Eureka or not. And what seemed to be happening is that there is some kind of bottleneck in that so people without Eurekas, they went with the baseline intuition that something that's not planar cannot be a geodesic. And it's only among people who had had a Eureka that we found people who were able to overcome this initial wrong intuition. So that's one first sense in which we found geodesics to be, Eureka experience to be accurate. We also wanted to test whether they are accurate in a different sense, in the sense of coming out of nowhere. So if you remember the Poincaré quote, what he said is that the idea came to him without anything in his former thought, seemingly paving the way to it. So in other words, that this learning or this searching for a new concept happened in his mind unconsciously, and then it's just suddenly that the idea burst into his consciousness. And we wanted to test whether there is something like this, so whether we had some evidence like this. And to do this, we asked people not only to report their Eureka experiences, we also asked them to introspect and reflect about their learning and tell us how well they thought they understood the concept of geodesics. And what we found is that Eureka reports and confidence ratings so about their learning, they were actually related to different learning achievements, suggesting that there are really 2 different mechanisms at play here, and where some mechanisms, learning mechanisms that bring about Eureka experiences are not informing people's introspection about how well they learn, suggesting that they are not actually accessible to consciousness, or that they are unconscious. It's still suggestive evidence at this point, but I think it's interesting to consider because it brings a connection between 2 fields of mathematical cognition and consciousness, which is particularly interesting today, of course, because these are 2 fields where Stan has had major impact, but more looking ahead because maybe we can start and build from the theories that have been made about conscious and unconscious processes to perhaps take a new look at theories of learning and bring about new hypotheses about what could be this bottleneck, what could be this block that prevents learning. And here I've just made a cartoon example about this idea of bifurcation and transition between 2 different states, and perhaps the Eureka being the reflection that one such transition just happened. And I think I'm probably end with my time. 2 minutes, oh wow. So then I can talk about one paper that just recently came out that I found very beautiful. So this paper is about, so if you take it seriously that there's some unconscious learning that happens before the Eureka takes place, you should have some building up to the Eureka. And there's this paper that just recently came out in PNS from Tyler Margetti's group, where what they did is studying the Eurekas that come out in mathematicians when they are doing difficult math. And they studied mathematicians, as they say it, in the wild or in their natural habitat, which is in offices. And then they gave them problems and studied how they wrote things on the chartboard and how they interacted with the things that they had written. They also recorded whether these people had overt eurekas. And what they found is that the pattern of behavior of interacting with these different inscriptions that they had done becomes increasingly unpredictable around the Eureka. And this starts 2 minutes before the Eureka, which raises a chicken and an egg question. Is it that somehow they become stuck and they start doing erratic thing, and that leads to an Eureka? Or is it because already 2 minutes before the Eureka, something in their mind clicked and led them to the direction of the Eureka? That's still $1 million question. Voila, so I'll end here. I thank, of course, my co-author, and I also, of course, want to give a big thank you to Stan. And also to all the different members of SHFG at the early 2000s who contributed to make me what I am today. And perhaps it's hard to add to all the compliments that have been given to Stan, but I want to share one story that had made a great impression on me, which illustrates how Stan will try and bring out the scientist in all his students. And I remember this day when I was a second-year PhD student. I was a clueless PhD student. I had no idea what I was doing. And Stan comes to me and he says, "What is the scientific question you want to answer?" And I had no idea. But I felt that this was the most useful question that someone has asked of me. And I now repeat that question to students. And that's it.